Okay, so in this video, we're going to be talking about pulley system problems and how to apply Newton's second law of motions to problems that are involving a pulley system. So let's look at this first problem. A block of mass 2 kg is at rest, so this means it's not moving, on a rough horizontal surface. The block is connected to another block of mass 1.5 kg by means of a light inextensible string which hangs over a frictionless pulley. So these words light inextensible just means that this rope here is not adding anything to this problem, right? String which hangs over a frictionless pulley. The 2 kg block experiences a constant frictional force of 3.1 newtons when a force of 20 newtons is applied to the block, as is shown in the diagram below. Ignore the effects of air friction. So I've taken the time to draw the diagram, and let's see how we would solve this particular problem. So the first step that I would advise is to say, draw a free body diagram of this block and of this block, just so that you know what forces are acting, or just so that you know what forces are acting on each of these two blocks. So a free body diagram is basically a dot, right? You want to have a dot and you want to have arrows coming from this dot going in the direction where the force is facing. So if we look on this 2 kilogram block here, let me move it a little bit further down. Sorry about that. Okay, so if we look at this, at this 2 kilogram block here, there is a force that is pulling it to the right. That's this 20 Newton force. And then there is another force that is in this rope that is pulling this block downwards. So let's draw this in a free body diagram. So we put a dot in the center. So this would be a body diagram, while a free body diagram would just be a dot. And then let me say that there is the first force that I see here is a applied force that is pulling this object to the right. So it's basically facing the right. And this is my F. This is the applied force. And then we have another force that is pushing this object upwards. The reason why it's not sinking into the surface is because there is another force that is pushing this object upwards, and we call that the normal force. The normal force is the force that the surface applies onto the object. So this is the normal force. Other textbooks will just put a capital letter N, but it represents the same thing, capital N or Fn. But I just like using Fn to show that this is a force, the normal force. Makes it easier to remember. And then we have another force of tension, the tension that is in this rope because of this block, right? This force is pulling this object to the left, and it's a great force, right? So we're just going to put that, the tension force, we can just say Ft to show that this is tension. However, we are told that this block is rough. That's why there's lines there to show that this block is rough. And it also says in the problem that on a rough horizontal surface, and because of that, that means that we also have friction. And friction is a force that opposes a body in motion, and it's also a force that is going to the left, opposing this motion. So we also have another force of friction that is opposing this body of motion, and we call that F of F. However, when the applied force is acting on this object, sorry, let me just write this in white, and then this is F. When the applied force is acting on this object, it's said here that the 2 kg block experiences a constant frictional force of 3.1 newtons when the 20 Newton force is applied. So what they're trying to say is that there is a moving friction that is beginning to act of 3.1 newtons, and we call that the kinetic friction because this object is now moving. So this is F of K. So this is F of K. F of K being the kinetic frictional force that is this object is experiencing because of our applied force. And the last force that we have is the force that is keeping this object to the ground, because there's another force that is pushing it upwards. However, the reason why it's not just going upwards is because there's an equal but opposite force pushing it downwards. And these forces just basically cancel each other out. So we don't, so yeah, when we do the equation, these forces, yeah, they cancel each other out. They'll be zero. So they don't have any effect on this particular block. So here we're just going to have a downward facing force, and that is our force of gravity. So that's Fg. Another textbook could also call it weight. And all of these also, you could call this W, you could call this tension, you could call this the normal force, you could call this just capital F, right? And then the force of friction is, you need to put that it's F of K to show that F of K is the kinetic friction that is acting on this particular block. Now let's look at the 2 kg block, right? So this, so this was for 2 kg. And now I want to draw the free body diagram for the 1.5. So like I said, we must start with the dot in the center, and then we show the direction of the forces. Here we have this object is sitting in the middle of the air, so we cannot have a tension for the normal force, because there's nothing that is pushing on this object upwards. However, there is a force that is pulling this object downwards, right? And this force is facing downwards. The reason why this is hanging in the air, there's a force that's pushing it downwards, and we call that the force of gravity, right? So that's Fg. Like we say, this could also be called the weight force, but I just like using Fg. And then there's also another force that is pulling this block upwards. The reason why it started in the air just resting is because these two were balanced. However, when we started applying a force, the applied force here, this object starts moving upwards as this 2 kilogram block also starts moving to the right. This moves up, and as it's moving upwards, it's because of the tension force that is in the rope. Or we said that we can call this F of T, which is just basically the capital T for the tension force. So these are the two free body diagrams that we need for this particular block. Now let's calculate the acceleration. We say that since now we've applied a force to this particular block, let's now calculate the acceleration. And we're going to do this. This is where these forces here that we're calculating come in play, to say that, okay, we know that this and this are going to cancel each other out because they are balanced. So the only forces that are acting on this object are these horizontal forces. You can hear that this block is on a rough horizontal surface. So on this particular 2 kg block, we're only going to be using these forces here, the horizontal forces. However, here there is no horizontal forces, there's only the vertical forces. So in this particular case, we're going to be using the vertical forces. So let's calculate. So the way to solve this, right, if we want to calculate the acceleration, because we have two variables that we don't know what A is, and we don't know what the tension is. Everything else is given. If you look here, we have the kinetic frictional force, which is 3.1. It's given here. It's given here as 3.1 newtons. We have an applied force of 20 newtons. We have the mass of the first block, the second block, and that's basically all that we need. And now we need to calculate tension in this part and tension in this part. We can calculate the force of gravity by just saying mass times acceleration, but we also don't know the acceleration. So that's why I'm saying that we have these two that we're trying to find. So let's come down here. Let's say that on the 2 kilogram, let's start with the 2 kg block. On the 2 kg block, right, what do we have? We have, if we look at it, we have a positive applied force we're going to call F, and this force is pulling the object to the right. So this is positive. If we look on a number line, if we drew a number line here, this would be positive. All the forces to the right would be positive, and down would be negative, left would be negative, and top would be positive. However, what I always advise is to say that take the direction of motion as positive. So here the force applied is moving to the right, so that is the direction of the force. So take that as positive. So we can say that we have a positive F. And then what else is acting on this 2 kilogram block? We have this negative force of tension and this negative kinetic friction. So we're just going to say minus the tension force and then minus the force of friction. We can just use a small letter F. So Newton's law of motion, the second law of motion, has the equation F net is equals to ma. So that means you sum up all the forces that are acting on this on an object, and then you equate it to the mass times acceleration. So this is all the forces that are acting on this particular object, and we equate this to mass times acceleration. Let me continue down here. So we say that F minus T minus F is equals to ma. Right? So let's substitute. The force that is acting on this particular object is 20 newtons. So we're going to say 20 minus, what is the tension force that is acting on this object? We don't know. We're not given tension. So we just write minus T minus the force of kinetic friction that is given here is given to be 3.1 newtons, as we are told in this particular part. It's 3.1 newtons. And this, we don't need to write the end. This is equals to mass. The mass is 2 kgs times acceleration. So we don't know what acceleration is. So we just write 2a. And then what we want to do is that we want to subtract 20 minus 3.1 happens to be 16.9 minus the tension is equals to 2a. And we want to isolate tension to be alone. So let's take 16.9. Let's add 16.9 to both sides. Sorry, subtract, so that it's going to cancel from this side, and then on this side we're going to have minus 16.9. And so minus T is equals to 2a minus 16.9. However, we want this to be a positive tension, so we multiply both sides by -1, multiply this side by -1. So the tension is equals to 16.9 minus 2a. And you want to keep this equation because we're going to need it in a moment. Then now we look at, let me just make this a little bit smaller just for space. Okay, so we know that our tension is equals to 16.9 and we're going to need it. Let's look at this part now. We have two forces that are acting on this object. The direction of motion for this block happens to be upwards. So in this particular case, and the tension is facing upwards, so because of that, our tension happens to be positive. So we have a positive tension because F net is equals to ma. And here we have the sum of all the forces. We have a positive tension, and we are subtracting the force of the weight force component. And we say that weight happens to be mass times the gravitational constant, which is 9.8. This is equals to mass times acceleration. And now we substitute in the values that we know. We don't know what the tension is, so we write it as it is. But we do know that the mass is 1.5. And the gravitational constant is 9.8. This is equals to the mass is 1.5 multiplied by a. So then we just group the like terms. So 1.5, if you check it in your calculator, multiplied by 9.8 will be T minus 14.7. And this is equals to 1.5 a. And then we just want to move this 1.5, this 14.7 to the other side. So we can do that by adding 14.7 to both sides. And this will be T, the tension, is equals to 1.5a, and then we add 14.7. So now we have our two equations. We have, this is the first equation, and this, so this is 1, and this is 2. And we need both of these equations. Now because T is now we have a value of T here and a value of T here. And if you look in the diagram, the same tension that is resisting this object to the back is the same tension that is moving this object to the front. So it's basically the same tension. The tension that is experienced on this block, on the horizontal part and on the vertical part, happens to be the same. So we're just going to come here and then equate the two values of tension. So 16.9 minus 2a is equals to 1.5a plus 14.7. And then what do we do in this particular case? Then what we want to do is that we want to take this 2a and move it to this side because it's going to become positive. And then we take this 14.7 and move it to the left. Now we cannot have a negative acceleration. That's why I want it to become positive. So this will be then 16.9. And then we take this 14.7. It becomes a minus 14.7. And we equate it to 1.5a. And then we add 2a. So on the right, you can see that it's going to become 1. It is going to be 1 plus 1. 1 plus 2 is 3. 3.5. 3.5a. And then on this particular side, it's going to become 2.2 because of 9 minus 7 will give us 2, and then 60 minus 14 give us 2. So this is going to be 2.2. So 2.2 is equals to 3.5a. And then what we want to do is that we want to divide both sides by 3.5 so that we isolate a. And a would be the answer that you get when you say 2.2 divided by 3.5. Which is equals to 0.63 meters per second squared. So that's it for this particular problem. We could also, however, just add what the tension of this particular block, well, what the tension in the rope is. And to do that, we just say tension is equals to 16.9, which is this. This is what tension is equals to, this part here. Why is it so thick? Let me just tone it down. This part here, right? So T is equals to 16.9 minus 2a. What is 2a? What is a? Sorry, a happens to be 0.63. So we're just substituting at this point. And this is equals to 16.9 minus this times this. So the answer that you're going to get when you subtract this into your calculator, you're going to get 15.64. And that's in newtons. So what I want you to note is that this force of tension does not exceed the applied force. It's less than the applied force. That's the only reason why we're able to move to pull this object to the right to 20 newtons, because the tension that is in the rope is less than the tension that is less than the force that is being applied. If we were applying 15 newtons of force as our force applied, and remember, this 15 newtons of force is supposed to move the first block and the second block, and it was not going to be able to move both of these blocks because it was not greater than the tension that is being experienced. Remember, we have tension, and the reason why the acceleration is so small is because we have tension that is acting on this block, and we also have friction. And we add, when we add tension plus the friction, our tension in this case is 15.64. If we add 3.1, which is our force of kinetic friction here, it's not going to exceed the force that is being applied. So that is why we can say that this object is moving to the right and it is accelerating. So that's it for this video. I don't want to make these videos far too long. I'm going to make another video with a different set of problems. So thanks for watching. Okay, so in this video, we're